All right, guys, welcome to today's class. Today, we're going to continue where we left off and start with 0.46. Hopefully, start the new chapter as well. In the triangle ABC in the diagram below, D and E are points on the side AB and F and G are points on the side AC, such that AB is equal to DG is equal to GB equal to BC equal to CE equal to EF is equal to FA, a bunch of isosceles triangles. Find BAC. Let's get to try this question and tell me answer to count. All right, let's get to the question. This is a little bit pretty hard question, all right? There's a bunch of sides, no angles, not really that much anything. But what we can do is utilize these sides since they're all equal. We have to find a bunch of isosceles triangles. And we do see a lot of isosceles triangles. So if we're trying to find BAC, we'll just let X be equal to BAC. All right, this will be X. Now notice that EF is equal to FA, clearly. So this is also X. And this is 180 minus 2X. All right, from here, you can also notice that. Notice that this is we can find this angle also too. It's gonna be 2x. But these are isosceles triangles, so ECF is equal to CFE. They're both 2x. So this angle is 180 minus 4x. And finally, not least, we want to find if we find these angles, C and B, or BCA and ABC, we're basically done since we can find what X is. Because from here, we get that these two are equal and the result follows. All right, let's see what we can do from here. All right. Hmm. Well, can we prove that these two triangles are the same? Hmm. Well, let's see. EF is equal to EC. Yes, we did that. Okay, so now also has C and CE. Oh, we can see it. From here, we get that this is 3x. Oops. We want whenever you're trying to look for a bunch of sides and there's like almost none angles and you're asked to find an angle, this means that there's like a bunch of angles which are in terms of one angle. For example, in terms of BAC. We get that from this equation. This will become CB is equal to 3x. Since 180 minus 4x plus x is 180 minus 3x. But then add all add BEC, CEF, and FEG all up, you get 180 degrees. So we get that BEC is 3x degrees. But we know that BC is equal to EC, so they're both 3x degrees. So this means that BCE is 180 minus 6x. Now, then BCA is just 180 minus 6x plus 2x, or 180 minus 4x. And we also have CBA to be equal. Oh, wait, hold up. DE are on the opposite sides. I'm making sure these are isosceles. If we don't know that they're isosceles, then of course that's not going to work. Hmm. Oh, but we also know this is 3x, this is 3x. But let's see what about this one. CBCG. All right. Hold up. This is clear up the board real quick. We can argue similarly that since we know this is 2x, this is 2x, this is x, these sides are equal, this is x, this is x. Get a bunch of angles. Let's see. This is also 180 minus 2x. This is 2x. Alright, so we get that uh both these angles are the same, so these are congruent, or that these are isosceles, which is true. Then we get 180 minus 4x plus 180 minus 4x plus x is equal to 180 degrees. Solving gives you negative 7x is equal to negative 180, or x is 180 divided by 7. All right. So what is the main idea? Well, we're just gonna find the angles, and there's multiple different ways you can do it. You can find BCG, that's in one way. But what I did is just find the angles, trace the entire triangle for angles, and then what we do is that try to find it to try to show that this is isosceles, which clearly happens since these angles are all the same and we got two congruent sides, and this follows by SAS. Alright? And then we can come out to show, remember what we said, ABC and BCA are then both 180 minus 4x, and add that to with the x gives you 180 degrees, and then solving for x gives you 180 divided 7, or 25 in 5 seconds. Alright? Now let's move on to 3.47. In the diagram below, DCE is equal to EZY, CYE is equal to AYE, and ED is parallel to YC. Prove CD is equal to DZ minus CY, and there's the diagram. I'll just gonna return this question and tell me answer through chat. This might be using a lot of congruent triangles or parallel lines too. All right, let's get started with this question now. So basically, how will we approach this? We want to prove that CD is equal to DZ minus CY. But how is this possible? How can we come along to do this? Well, one way to think about this is we're replacing sides. That's a very key important part. Well, we have DZE is equal to DZE is equal to EZY and CYE is equal to AYE. All right. And ED is parallel. Okay. And we want to show that CD is the difference of these. All right. What can we come along to prove that? Well, since ED is relative to YZ, we have DZE. DZE. Okay. We have DZE. That angle is equal to EZY as well as ED. Why? Because of parallel. Because this is a transversal. These are transversals. So these angles are the same. So they bisect the same exact. Basically bisect the same. Well, the same exact. Well, these are not taking. This one's not parallel, but these basically bisect the same exact angle. All right. It's easy to see that uh this angle is equal to this angle through transversals. All right. As well as we know that DE. Then from there, just know that DEZ DZ is an isosceles with DEZ to EZ. I'm at DE equal to DZ. Similarly, we can get that YED is equal to AYE is equal to CYE with the same exact reasoning. And we can get CEY is isosceles with CE is equal to EY. Now we do substitutions. We can see that clearly. We can clearly see that CD is equal to DE minus C. But, however, we do know that DE is equal to DZ. And then CE is equal to EY. I mean, CE is equal to CY. Alright? And then from here, it's done. So these are isosceles triangles, and so is this one. It's substitution. Alright? Now it's 1 to 3.48. Describe under what conditions, as they say, congruence works. In other words, when is it true that if AB is equal to XY and BC is equal to YZ and BAC is equal to YXZ, then we can immediately conclude that ABC is equal to congruent to XYZ. It only happens when the triangle is an iso and what do we call it? Yeah. This only happens when the triangle itself is right, as well as if the four lengths are the same. All right. That's one way to happen. All right. It also works when we have an isosceles triangle. All right. And we know that these angles must be these have two sides that are the same and an angle that are the same. But since they have two sides that are the same lengths, then this means that we know that the base angles are the same as well as the vertex. So it's easily proven by SAS. Isosceles. Might be spelling this wrong. Hopefully not, but hopefully this is the right spelling. But it's only gonna possible when it's right, which we have the right HL, I believe, high angle hypotenuse leg, I believe. But why is that true? It's because if we have an angle of a triangle, then we immediately know that the other angle is 90 minus that. As well as we know that there are two sides that are the same, so it's easily proven by SAS. Last one to 3.49. In the diagram below, XYZ is equal to AXC is equal to 90 degrees, AX equals XY, and XZD is equal to YZD. Prove that ZD is perpendicular to AY. There's two hints, and how do we approach this? Well, note this. There's a cool thing. there's a cool note you can do is that notice that we want to prove that the ZD is perpendicular to AY. So the entire purpose is just angle chasing. Or prove that it's isosceles. We can might as well just also prove that this triangle is isosceles. Well, just prove that the two base angles are the same. That's one way, right? So how do we come to prove this? All right, let's see. Hmm. Let's maybe try angle chasing. All right, that's the first thing that comes up to mind. And we also know that these angles are the same. All right. Well, if these angles are the same, and we don't even know that it's perpendicular, what can we get from this? Well, we just need to prove that these two sides are the same. Hmm. Similar conclusion. C. This angle, notice as x, this is going to be 90 minus x. But if that's 90 minus x, then it's going to be 90 plus x. This angle is 90 plus x. We know that this angle is x. So, this just becomes 90 minus 2x. That's the angle. Okay. So what else? Well, we gotta extract more from this question. We know that ax is equal to xy, alright? Since we know that this angle ax is equal to xy, and these angles are the same, let's note this is y, alright? Let's see. What else can we grab from this? Well, this is gonna be 90 minus y clearly. This is 90 minus y clearly. And this is also gonna be 90 minus y, obviously. And we have these two angles. What are these two angles, right? Well, we know that this is 90 minus x and these angles are the same. So this must be, remember, this is also y. That's 90 minus x. And this is going to be y then. All right. And what is this? This is going to be 180 minus 2y. Or this is going to be 90 minus 2y. And this is going to be y, so this is just y. Wait, am I doing it really? No, 90 plus y. My bad. This is going to be 90 plus y. So far, we haven't got a single thing from the English. So what could we have done wrong here? Maybe we need to try to find congruent triangles now. Because we clearly see that angle chasing is not working. So you might as well try to find some congruent triangles. Alright, so let's denote the intersections then. Let be B and this one C, alright? Now, what can we do from here? Well, we obviously need to prove that BCZ and YCZ must be the same. So we take the advantage of the isosceles. We actually need to take advantage. So from here, we can get that ZBC is going to be 90 minus Z. As we denote, let's put this as Y for now. Y, this one's 90 minus Y. 90 minus Y. We want to prove that this is also 90 minus Y. Oh, wait, forgot. I actually already proved that part. Oh, wait, shoot, my bad. Because we already said this is Y, so this is also 90 minus Y. And then from here, we get, this side is the same, and these angles are the same, so we have AAS. But yeah, that's a valid congruent statement. And from here, it's just saying these two triangles are the same. So this is perpendicular. And that problem is solved. Alright? That's one way to do this. So we're done. So sometimes you can overlook stuff, alright? We can kind of overlook stuff. As we already saw that this is y and that's y. We get 90 minus y on each one. And then the triangle's up. So we kind of overlooked. I kind of overlooked. Right? Anyways, that's how you solve this question. You won't find congruence, and a point is not to overlook a question. Make sure you read every single reason carefully, because I only looked at the y and forgot all about the zy. I meant zyc in this case. All right. Now let's move on to 3150. Draw equilateral triangles BCBCAQABR outside ABC. Try outside. I mean BCBCAQABR outside triangle ABC as shown in the diagram. Prove that AP is equal to BQ is equal to CR. I'll just try this question and tell me as to do chat. All right, let's get started with this question. So we want to prove that AP is equal to BQ is equal to CR. So how do we come about to do this question? I wonder. Let's see. Well, one thing that we can do is prove that there's a bunch of sides or triangles that are congruent. All right, that's one way to do it. We want to prove that AB is equal to BQ is equal to C. I remember this was a very. There was a theorem about this, right? I think it's like Napoleon's theorem or something. I believe that is the theorem. All right. Well, let's get started. We notice that RB. Let's put this as. What do we put this as? I'm just gonna put this as S. Well, we notice that RB is equal to AB since it's an equilateral triangle, and so RBC is equal to RBA plus ABC. Clearly, this is just splitting it apart. And we also know that this is just going to be PBC plus ABC or PBA. It's just a rearrangement of angles. And we notice that BC is equal to PB. We have RBC ABP by SAS. When we get RC is equal to AP. And similarly, you have AB is equal to RA. And BAQ is equal to BAC plus CAQ is equal to BAC plus RAB is equal to RC. This is just basically doing the exact same method to the two other triangles. You get AC is equal to AQ, and then RC is equal to BQ. And then it's just now just to combine all of this together to get the answer to this question is just AB to BQ to CR. So it's just applying these angles, basically angle substitutions, putting one angle as equal to another, and then and also with sides to prove with congruency. That's the whole point of the problem. Now also we're doing 3.51. I'll just do a quick overview, right? So we have two sides and an angle, all right? Two sides and an angle. And we have one. So this really clearly just S is A. Example why S is A doesn't work, all right? I won't do the full question, but I'll give you the answer. It's going to be 100 degrees because there's going to be two possible ways. We have that this is 40 degrees, and we have AB is 13, and each of these are 10. Then afterwards, you just put these together. You notice that there's going to be two possible angles for this. One angle like this, one angle like this. And then you can basically from here is just test and test to see you. Basically, you just put in as an equation. Basically, that's how you're supposed to do it. And then you find the two values and then find the answer. All right. Through angle chasing, obviously. All right. So that's it for today's class. Hope you guys have a wonderful weekend, and I'll see you next week. Bye.